Alright everybody, welcome back to the series on statistics. I was going to make a video on moment generating functions, but I realized that there's kind of an important property that I sort of skipped over. It's going to be important to deriving the moment generating function for the normal distribution, which is ultimately going to be important for proving the central limit theorem. But there's sort of this intermediate step, which is that we need to sort of solidify this connection between the generalized and standard forms of the normal distribution. And I thought it would be kind of fun to do that in a separate video. This does have its own sort of implications. There's a thing called a Z-score that we're going to talk about in this video because it's very fitting. But I thought it would be kind of fun to do a formal proof for this, just to sort of see what that's like. A lot of times in the series, I try to focus on derivations so that we can see where formulas or theorems come from. But I don't really do formal proofs of them. I do sort of derivations. Just to give a sort of intuition. In this video, I wanted to do sort of a semi-formal proof so you guys could see how that is. Alright, so let's get started. Our goal in this video is going to be to show a connection between this generalized form of the normal distribution and this standard normal distribution. And so, in keeping with that, we have a proposition here. It says, if x is a normally distributed random variable with a mean of mu and a variance of sigma squared, then the claim here is that x minus mu over sigma is a normally distributed random variable with a mean of 0 and a variance of 1, otherwise known as the standard normal distribution. Okay, so we're going to prove this. I'm going to do a good portion of this verbally because I have horrible handwriting, and if I was sitting here writing out all the steps, there's typically a lot of writing involved in these mathematical proofs. Then I think everybody would get bored watching, and I think it would be barely legible, if legible at all. So I'm going to do a lot of the reasoning out loud, and I'm only going to write down most of the math components. Alright, so let's get started with a formal proof. The first thing I will say is to let z be a normally distributed random variable with a mean of 0 and a variance of 1. This is very conventional. We very typically denote the standard normal distribution, which is exactly what this is, with the letter z. And then the actual method that I'm going to take to prove this is I'm going to try to show that the cumulative distribution function for this distribution is equivalent to the cumulative distribution function for this distribution. If we could show that the cumulative distribution functions are equivalent, then we know that the probability density functions are equivalent. And if you have two distributions with the same probability density function, then they are identical distributions. So these would then be the same random variable. And so I guess the first step here is to try to figure out what the cumulative distribution function of this random variable is. And we don't actually know that, but we do know what the cumulative distribution function for this random variable is. Or maybe we don't. I know that in my video on the normal distribution, we covered the probability density function. I'm not sure if we touched on the cumulative distribution function. I remember showing it in Desmos. But if we don't, then let's just remind ourselves. So this is our random variable x. We know that x has a probability density function of, let's see, we would say f of x, I'll denote it this way, is going to equal 1 over 2, or 1 over the variance, or the standard deviation multiplied by the square root of 2 pi, multiplied by e to the negative 1/2 x minus mu over the standard deviation squared. This is our probability density function for a generalized normal distribution. And then we know that the cumulative distribution function, let's see, what would that be? The cumulative distribution function, which I'll denote with the capital F of x, this is equivalent to saying the probability of the random variable being less than or equal to x, which is our input to the function. So I'll make this x a little bit smaller to sort of make that distinction clearer. This is the probability of our input to the function, the probability of our random variable being less than or equal to that. And so what is that equal to? If we understand our properties of these probability density functions, this is just the area under the curve from negative infinity to, in this case, up to x. And the reason we're doing negative infinity is because this probability density function is defined for all real numbers. Okay, and then we're just integrating over the probability density function. We only need to make one little change here. 2 pi e to the negative 1/2. which is that because we're using x here, we need to instill a dummy variable. So I'll use the letter t, just in keeping with convention. And so this is our cumulative distribution function here for our generalized normal distribution. Now, what I want to consider is that if we want the cumulative distribution function for this distribution, by the definition of a cumulative distribution function, this would be equal to the probability of this random variable here, x minus mu, this is big X here, over sigma being less than or equal to some input to our function. This is the definition of the cumulative distribution function here. This would be or I guess this isn't the definition, but this would be equal to our cumulative distribution function for this distribution evaluated at x. And so that's what I mean when I say that's the definition. But what is this actually equal to? I'm sure you will agree with me if you manipulate this inner part here algebraically. This is exactly the same as saying that this is equal to the probability of the random variable being less than or equal to sigma x plus mu. These two statements are equivalent. These probabilities are equal. And this is just the cumulative distribution function for the distribution that we already know, but evaluated now. Instead of at x, we're evaluating it at this right here. We're evaluating it at sigma x plus mu. And so now we can actually have the means to solve this. This is equal to the integral from negative infinity to sigma x plus mu of 1 over sigma square root 2 pi e to the negative 1/2 x minus mu, or I guess forgot about the dummy variable. We need t minus mu over sigma squared dt. Sort of move things over here because I want to be very clear about what we're saying here. We're saying that the cumulative distribution function, let's see, maybe I need a little bit more space. The cumulative distribution function for this random variable here, for x minus mu over sigma, the cumulative distribution function for that variable evaluated at x is exactly equal to the probability of the random variable minus mu over sigma, that's this, is being less than or equal to x, but this is equivalent to the probability of x being less than or equal to, or the random variable x being less than or equal to sigma x, our input, plus mu. And we can evaluate this in terms of the cumulative distribution function for the distribution that we already know. And that's just this integral here. And so if we want to figure out what this is, we just need to reduce this integral. And we can make some progress in reducing this integral by simply applying u substitution. And so I'll just write by u substitution, by u sub. Let u equal, I want to get this exponent here cleaned up, so I'll let this equal t minus mu over sigma. And really the reason I want to do this is because ultimately what's our goal here? Our goal is to get this in terms of the cumulative distribution function for the standard normal distribution. And so what does that look like? Well, that just has one variable up here, and it doesn't have this sigma here. And what's going to happen if I use u substitution to turn this exponent here into just one variable? What's going to happen is then du is going to equal dt over sigma, and dt, here this part, will be equal to sigma du. And so by making the substitution, I will clean this up and turn it into just one variable, and I will also simultaneously get rid of this sigma here by multiplying by sigma du. And I'll be left with something that looks very similar to the cumulative distribution function for the standard deviation. But we do need to make sure that the bounds on this integral here are taken care of as well. And so upper bound on this integral, what is that going to be? Well, if I plug this in for u here, I'll get u is equal to, plug this in for t, because this is in terms of t and we want it in terms of u. And so this is going to be sigma x plus mu minus mu over sigma. I'm sure you would agree that the mu's would cancel. You divide by sigma, we just get x. So that's going to be the upper bound. Well, what about the lower bound? The lower bound on this integral, I kind of missed that. The lower bound on this integral, we would plug in, it looks like negative infinity minus mu over sigma. I'm sure you would just agree that this is also negative infinity. And so with all of this taken together, we have shown that the cumulative distribution function for this random variable minus mu over sigma, evaluated at x, this is just equal to the integral from negative infinity to x of 1 over the square root of 2 pi, because the sigmas are going to cancel when I do the u substitution, and then this is going to be e to the power of negative 1/2 u squared du. And this is exactly equal to the cumulative distribution function for our standard normal distribution evaluated at x. And I'm sure this looks familiar. I'm sure that makes sense. And so with this proof, what we did, I guess we could write a fitting conclusion, but basically we set out to show that the cumulative distribution function for this random variable here was equivalent to the cumulative distribution function for the standard normal distribution. We started with the cumulative distribution function, we made some clever observations about the probabilities, and then we ultimately wound up showing that the cumulative distribution function for both distributions was identical. And so from that we know, thus, x, our random variable, minus mu over sigma, is equal to z, which is our normally distributed random variable with a mean of 0 and a standard deviation or variance of 1. And so this is a sort of semi-formal proof of that. So this sort of directly leads us into this concept of z-scores. So we have what we just proved, which is that if x is a normally distributed random variable with a mean of mu and a variance of sigma squared, and z is a randomly distributed normal variable, or normally distributed random variable with a mean of 0 and a standard deviation variance of 1, this is just a standard normal distribution, then their cumulative distribution functions are equivalent. But equivalently, we could say that this is exactly the same thing as saying the probability of x minus mu over sigma being less than or equal to x is exactly equal to the probability of z being less than or equal to x, where the z is that standard normal distribution. And so what does this allow us to do? It allows us to compute a value based on our general normal distribution here, where if we take the output of our random variable here according to this general normal distribution, we subtract the mean, and we divide by the standard deviation, then that's going to give us a quantity called a z-score. And then if we take that z-score and plug it into a standard normal distribution, it allows us to make statements about the original distribution based off of computations involving the standard normal distribution. Right, so that might be a little confusing, so I have just a very simple basic problem here. Just to sort of illustrate this, we have if x is a normally distributed random variable with a mean of 3 and a standard or a variance of 2, and then what is the probability that x is greater than 4? And so how would we solve this problem? Well, we have two options. We could plug in 4 to the standard deviation, or plug in 4 to the distribution here, to the cumulative distribution function for this variable. And so we could take we could say that this probability is going to be equal to the integral from negative infinity to 4 of 1 over the square root of 2, or I guess this would be the square root of 4 pi, because that square root of 2 would go into this square root. We have 1 e to the power of negative 1/2. We'd have x minus 3 over the square root of 2 squared. And so if you evaluated this integral here, this could be dx. If you evaluate this integral, this will give you that probability. But there's another option we could take here, which is to compute what's called a z-score. And so the z-score is just going to be equivalent to this value right here. And so in this case, it's going to be 4, because that's our value for x that we're interested in. And then we're going to do 4 minus the mean divided by the standard deviation. The standard deviation is the square root of 2. And so this is going to be equal to 1 over the square root of 2, which is just root 2 over 2. And now what this allows us to do is to say that this probability is also equivalent to the cumulative distribution function of the standard normal distribution here. To put square root of 2 over 2. And then now it's just the standard normal distribution. So this is going to be the square root of 2 pi e to the negative x squared, or negative 1/2 x squared dx. And so if you were to plug these two integrals into Desmos, for example, they would give you exactly the same answer because we just proved that this probability is equivalent to this one. And so all we're doing is computing this value here and then plugging it into a standard normal distribution cumulative distribution function. But there is one part of this problem left, which is that we're asked what the probability is that x is less than or x is greater than 4. And this is going to give us the probability of x being less than or equal to 4. And so our answer here is going to be 1 minus this integral here. And so the probability of x being greater than 4 will be equal to 1 minus, and then you could use either one of these integrals, but just for the sake of demonstration, I'll use this one. So we want to plug that one in here. And you can evaluate this in your calculator or Desmos, but if you plug that in, it looks like you will get about 0.2397. So somewhere about 2397. So I hope that made sense. I hope that kind of explains what a z-score is. Essentially, it's telling you how many standard deviations away from the mean a particular output of your experiment would be. But the reason that quantity is useful is because based off of what we proved in the beginning of this video, it allows you to make statements off of any normal distribution with any mean, with any standard deviation, based off of the standard normal distribution just by computing this value here, which we call a z-score. And this might seem kind of like an antiquated idea, and in some aspects it kind of is. For instance, you could have just used this integral to solve this problem, and you had no reason to convert to a z-score and then use the standard normal distribution. But if you harken back to a time before supercomputers in every calculator and iPhone, then the way that old mathematicians had to solve these problems is they had a rigorous because these integrals are impossible to evaluate, you have to estimate them. And so they had giant tables full of particular values of the area underneath the standard normal distribution centered at 0 with a standard deviation of 1. And then they had to compute z-scores off of other normal distributions in order to compute probabilities based off of them. So that was actually necessary before. Now in this day and age, it's not necessary. There are several shortcuts you can use, and we have Desmos, we have graphing calculators in RStudio that are capable of computing any of these probabilities. We don't need to convert to the standard normal distribution. It's not strictly necessary. But there are other places in which this z-score idea is useful. We're going to see these crop up in confidence intervals and hypothesis testing, which is going to be coming soon in this series. There's a couple more things we need to cover. I actually think now is an appropriate time to do that. So what's coming next, I think you guys have, if you're following along in the series, you might realize that this is a very laborious undertaking. And if you have thought maybe like, oh, there's no way that you have to write out this entire expression into Desmos every time you want to compute one of these things, especially knowing that these distributions are so common, this really can't be the way to solve this. And you're correct. There are several faster ways of solving these problems that really aren't faster. This is exactly what they're doing, but they've sort of cut out a lot of the mathematics to where all you have to do is plug in a mean, plug in a standard deviation, and you can use a tool such as your graphing calculator or RStudio in order to compute these integrals much faster. So I've sort of shown all the details and the mathematics behind these normal distributions, but I haven't really given the tools to efficiently solve problems involving the normal distribution, involving normal distributions. I will do that, but I have a couple more theory videos I need to make first. So what's coming on the horizon, the next video in the series, should be about moment generating functions. Now we have enough information to derive the moment generating function for the normal distribution, which is important. And the reason that that's important is because the next video in the series is going to be proving the central limit theorem. which you need moment generating functions to do. But they're useful in their own right. So those two videos will be next, moment generating function and the central limit theorem. After that, I will make a video on how to actually solve these normal distribution problems efficiently using graphing calculator or RStudio. And then after that, we'll move on to confidence intervals and hypothesis testing. And that's probably going to be the end of the Statistics 1 series. So with that said, I hope you guys enjoyed this video. Hope it was informative. And I'll see you guys in the next one.